Welcome to the deep dive. Today we're really getting into the weeds on some advanced stuff. We're looking at the internal development guidelines and, well, the actual code for a very specialized offensive framework called LazyOwn, super OPSEC focused.
That's right. And when you look at tools like this, LazyOwn, tools built by groups who are really serious about evasion, persistent evasion, you kind of stop looking at just features. You start looking at the constraints.
Constraints.
Yeah, the rules they have to follow. So for you listening, our mission today is to understand the, let's say, the technical cost of modern stealth. We're dissecting the absolute rules, the memory tricks, the custom loaders, the whole philosophy needed to build code that just vanishes in modern detection systems.
Okay, so let's jump right in. We've got this developer prompt, right?
Yep.
Like their internal rulebook.
Yeah.
And the very first thing, the big one is absolutely no standard C runtime. No CRT at all.
Yeah, it's foundational. Really shows the level they're operating at. Why ban it? Well, security products, they don't just hunt for known malware code. They look for dependencies, for signatures.
Right.
Every standard function you'd normally use thinkmalloc for memory or strictbep for comparing strings, even basic print for output, all that stuff, introduces code, data, that has a known footprint. It's predictable.
So, okay, let's say I'm coding a module for this framework. I need to copy some data. If I just drop in a standard MengPy, what's the actual risk there? Why is that so bad?
You're basically introducing a known library call. When your code uses MengPy, the compiler links it often to a function in a standard library, and that leaves a trail, maybe in the import address table or just how it references memory. Security tools, they fingerprint those entry points constantly.
Ah. Okay, so it's like showing up to a stealth mission carrying a big, standard issue, brightly colored toolbox, not exactly subtle.
Exactly that. You're forced to build your own tools, basically from scratch, using low-level system parts. Need to copy memory, no MempPy. You have to dynamically find, say, RTL copy memory from ntdll.dll at runtime, or maybe use an internal helper they wrote, like mime-MempPy.
And for output?
Gotta use their specific function, beacon print. It forces everything through runtime resolved system calls. That makes static analysis incredibly hard, and it dodges all those common CRT signatures everyone looks for.
Okay, that makes sense. That core rule, that philosophy, it directly leads to the complex machinery, doesn't it? Let's look at the first bit of that machine, the COFFLoader engine. This thing handles beacon object files, BOFs. What's interesting about the runCoff function here?
Well, what's really fascinating is just how much work goes into resolving a single Windows API call.
Yeah.
Say the BOF needs VirtualAlloc. It doesn't just look up the string VirtualAlloc.
How then?
It uses symbol hashing, specifically the DJB2 algorithm.
So wait, instead of the actual function name string, the code just has a number, a hash, that represents VirtualAlloc.
Precisely, a 32-bit hash.
And what did that buy them? I mean, in terms of evasion.
It defends against basic forensic techniques. Imagine an analyst dumps the memory of the process. They search for strings like VirtualAlloc, get proc address, common API names. They won't find them. They'll just find a list of these seemingly random 32-bit numbers. Only the framework's own loader, with its internal symbol table, knows that this hash means VirtualAlloc. It's obscurity, yeah, but done very systematically.
Okay, so it resolves the functions using these hashes. Then it handles the file structure itself, right? Reads the COFF section headers, uses VirtualAlloc to get memory, makes it executable with page executor add write.
Right, gets the code ready to run. But making it run stably? That brings up the biggest headache, really, for loading code in modern 64-bit Windows. Relative 32-bit relocations. REL32.
REL32. Okay, why is that such a huge challenge when you're loading code into, potentially gigabytes of memory space?
Okay, think of it like this. Code often needs to jump from one spot to another internally, like instruction A needs to jump to instruction B. It often uses a very short, efficient jump based on a relative offset, how many bytes forward or backward, a 32-bit offset. But in a 64-bit process, your memory space is vast. Instruction B might be way too far away from instruction A for that 32-bit offset to actually reach it. It's like trying to give directions using only miles when the destination is thousands of miles away. The jump instruction simply can't encode a large enough offset
And crash.
And crash, or just unpredictable behavior. The jump fails.
So the relative jump calculation is too small for the vast 64-bit landscape. How does the LazyOwn loader fix this? This seems critical.
This is where it gets pretty clever, very low level. The loader detects when a REL32 jump target is too far. Instead of just letting it fail, it dynamically allocates a tiny chunk of memory near the instruction that needs to jump.
Okay.
And in that tiny chunk, it writes a few bytes of executable assembly code. This is the trampoline.
A trampoline, what does it do?
It's really simple, just 6 bytes, typically owned by 64. MOV racks, target address, A and B racks. It loads the full 64-bit absolute address of the real distant target into the racks register, and then it jumps to the address in racks.
Ah, so the original short jump doesn't go to the final target anymore.
Exactly. The original failing 32-bit relative jump is patched to point to this nearby trampoline instead. The trampoline then executes the long 64-bit jump successfully. It's like building a little bridge on the fly. Ensures stability, avoids crashes, and doesn't introduce any big, obvious new components.
That's wow. It's like dynamically repairing the memory map just for this one jump. Okay,
Indeed.
so sections loaded, relocations patched with trampolines if needed. Then the BOF's main function, boy go, char args into ALN, finally gets called using this custom call-line function. I'm guessing that alignment part is also about stability.
Absolutely. The by64 calling convention is really strict about stack alignment. The stack pointer needs to be aligned to a 16-byte boundary before most function calls, especially those involving certain types of instructions or parameters. If it's misaligned when you call the BOF's go function, you could get subtle data corruption or just random crashes. Very bad for OPSEC.
Right, a crash is the loudest possible alarm.
Exactly. So call aligned is just a small wrapper that makes absolutely sure the stack is perfectly aligned before making that final jump into the BOF code. Stability first.
Okay, we've seen the intense discipline needed just for these small BOF modules. But now we need to shift gears, scale way up. We're moving from running little code blobs to running an entire Windows executable, a PE file, completely from memory. This is the job of the Black Basalt multi-stage PE loader.
Yeah, this is a huge jump in complexity, a full PE file. You're talking imports, sections, maybe resources, relocation tables, potentially a lot more code and data. The process laid out here is definitely high stakes. It's described as the 3-stage process, kicked off by fetching resources using that specific command line structure they mentioned. Host.port peer source cure resource.
Right, that structure tells it where to get the goods. Let's walk through Act 1, the download.
Okay, so remember, no standard library is easily available. So the getData function has to dynamically resolve networking functions it needs, specifically from win-http.dll. We see things like win-httpopen, win-httpconnect, win-httpopen request, etc. being called directly.
And it grabs 2 things based on that command line structure.
That's right. The encrypted PE file itself from P source, and then a separate, likely much smaller, key file from key resource. And interestingly, they even hardcode a user agent string, LazyOwn Downloader 1.0.
Huh. Why bother with a user agent? If you're trying to be stealthy, wouldn't sending no user agent be quieter?
Not always. Sometimes having no user agent is actually a red flag for network monitoring, or some web servers might just reject requests that lack one. By putting in LazyOwn Downloader 1.0, they ensure the download works, but they also control exactly what that footprint looks like. It's a calculated choice, balancing stealth, and just making sure the download actually happens.
Okay, makes sense. Trade-offs. So the 2 pieces are downloaded. We move to Act 2. Decryption. This uses native Windows crypto functions, also resolved dynamically, this time from advapi32.dll.
Right, and it's a careful sequence to avoid having the raw decryption key just sitting in memory. First, it gets a crypto provider context using cryptacquire context W. Then, crucially, it doesn't just use the downloaded key file data as the AES key.
No, what then?
It takes the entire content of that downloaded key file and feeds it into a cryptographic hash function, specifically SHA-256, using cryptCreateHash with KeyLGSA-256 and then crypthash data.
Okay, so the key file itself isn't the key. It's just input material for generating the key.
Exactly, the raw material. That resulting SHA-256 hash, which is derived from the key file data, that's what's used to derive the actual AES key. It uses crypt-derived key with KeyL256.
So the real AES key is generated on the fly from the hash. It's ephemeral.
Precisely. High entropy, generated just in time, never stored statically. Only after this whole chain acquire context, hash the key file data, derive the AES key from the hash. Only then does it actually decrypt the main downloaded PE file buffer using cryptocrypt. It's all done using native Windows functions, keeping the sensitive key material as transient as possible.
Very clever. Okay, decrypted PE in memory. Now Act 3, in-memory execution. But before they even allocate memory for the new PE, there's this preparatory step that sounds quite aggressive. Trying to unmap the original process's image base.
Yeah, that's a pretty advanced technique, often associated with process hollowing. The loader dynamically resolves ntonmap_view_off section from ntdl.dll, which is a low-level function, to remove a section of memory from a process.
Why do that? Why unmap the memory where the original program, the dropper or loader itself was loaded. Wouldn't it be simpler just to allocate new memory somewhere else?
It serves a couple of key purposes, mainly stealth and compatibility. By unmapping the original image, you're essentially erasing the footprint of the initial benign program that started this whole chain.
Cleaning the slate.
Right. And then, ideally, you allocate new memory at the same base address where the original program used to be, and load your decrypted PE there. This makes the new PE look more like the legitimate process that was supposed to be running. It can help bypass certain checks and potentially makes the PE's own internal code, which might assume it's loaded at its preferred base address, run more smoothly. It reduces the indicators of process injection.
Got it. So erase the old, load the new in its place if possible, then copy the PE headers, copy the sections into the newly allocated memory. The PE is almost ready. But there's one last trick, isn't there? The command line masquerading.
Yes, this is the final layer of deception, implemented using functions named masquerade, salmon line, and repariate. This is aimed squarely at fooling forensic tools and maybe even internal checks within the loaded PE itself.
Why hook things like getCommandLine or getCommandLine or even those compiler helper functions like getMainArg? They seem pretty basic. Why mess with them inside the PE you just loaded?
Because it's about controlling the narrative, the PE's perception of its own environment. When that newly loaded PE starts running, it's probably going to call getCommandLine to see how it was launched, what arguments it received.
And if it sees the real command line that launched the initial dropper,
That's a huge indicator for incident responders. It might contain IPs, ports, resource names, all the malicious details.
so the repary function goes into the PE's import address table. Basically, it's list of external Windows functions it needs to call, and it finds the entries for getCommandLine, getCommandLine, etc.
Exactly. And it overwrites the address of the real Windows function with the address of a custom hook function provided by the LazyOwn framework.
So when the PE thinks it's calling the normal Windows getCommandLine,
But it actually executes the hook function instead. And that hook function feeds it a completely fake, sanitized command line. The source code shows it's initialized to just whatever. So the PE itself and any tools inspecting its memory later will see this harmless command line completely hiding the real arguments used to initiate the attack. They're effectively rewriting the process's history in memory, in real time.
This whole thing, from the no CRT rule all the way to IAT hooking the command line, it's just an incredible example of blending really low-level binary manipulation with high-level deception tactics.
It really is. We've basically walked through a masterclass in survival within a monitored environment. They avoid signatures everywhere, resolving APIs dynamically, hashing names, using trampolines to ensure by64 stability, encrypting payloads, hollowing the process memory, and then actively lying to the payload about its own launch parameters via IAT hooking.
Yeah.
This level of meticulous control, it just shows that modern offensive development isn't just about getting code to run anymore. It's about achieving total customized control over the execution environment, over memory, over identity.
It really makes you think. If developers are already ditching fundamental C features like printfo, mengsepi, things programmers have used for decades, just to stay hidden, what's next? What other basic building block of programming might they be forced to abandon or radically reinvent in this constant cat-and-mouse game of evasion? Something to chew on until our next deep dive.